Welcome to the Joy of Architecture. Today, we're diving into something that's absolutely critical if you're building or running software in today's complex world, understanding what the heck is actually happening inside your systems.
Exactly. I mean, we've moved from simpler systems, monoliths maybe, to these highly distributed ones. Think microservices, cloud, container, it's everywhere.
Right. And that complexity just makes the old ways of checking if a server is up.
Yeah.
Well, it's not enough anymore, is it?
Totally insufficient. When a user clicks a button now, that single action might ripple across, I don't know, dozens of services. So how do you even know if something went wrong? And crucially, where it went wrong?
Yeah, you need that visibility, that ability to see inside, right? To understand the internal state just by looking at the external signals.
Yeah.
That's observability, isn't it? That's the core idea.
It is. And it's more than just monitoring if something broke. It's being able to ask why and how, even for problems you didn't anticipate, and doing it without having to push new code just to find out.
Okay, got it. And this builds on three main things. Pillars, you call them.
Precisely. The three pillars of observability: logs, metrics, and traces.
Okay.
Think of logs as like discrete events. This specific thing happened at this exact time, very granular.
Right, like a diary entry.
Kinda.
Yeah.
Then metrics are the numbers, the aggregations, how many requests per second, what's the average latency, CPU usage,
Yep.
that kind of stuff.
The big picture numbers.
Yeah, the quantitative view. And finally, traces. These follow a single request's journey through all the different services it touches. Shows you the path, how long each step took. Really good for understanding flow and bottlenecks.
Okay, so logs, metrics, traces, that's the foundation.
Yeah.
So our mission today in this deep dive is to explore 5 essential patterns that actually use these pillars to give you that visibility for reliable systems.
Yep.
We're going to unpack centralized logging, audit logging, distributed tracing, metrics aggregation, and finally, health check or endpoint monitoring.
Sounds like a plan. Let's start with maybe the most fundamental one, especially for debugging: centralized logging.
Okay, so simply put, what is it and why is it so, well, non-negotiable these days?
Centralized logging just means getting all your logs from every single service, every server, container, piece of infrastructure, you name it, into one central place. The problem it solves is fundamental in a microservice world. Like we said, one user action hits many services. If logs are scattered everywhere on each individual machine or container, well, good luck troubleshooting that. It's practically impossible.
Right, you'd be SSing into boxes all day.
Or trying to find logs from containers that have already disappeared.
Yeah.
You need that single pane of glass, one place to search, filter, correlate logs across the entire system to figure out what actually happened.
So it's like finding that one specific needle, but first you have to bring all the haystacks together.
That's a great analogy, yes. And the benefits are huge. Massively speeds up troubleshooting, reduces your mean time to repair, your MTTR. It also really helps with security forensics, understanding what happened during an incident. And it's often required for compliance, providing that auditable trail.
Plus, I guess once you have all that data together, you can do more with it.
Absolutely. Once logs are centralized and ideally structured, you can start analyzing them for performance trends, user behavior patterns, all sorts of insights.
But collecting all the logs from everything sounds
Yeah.
expensive.
And noisy.
Oh, definitely. That's the trade-off. The sheer volume of data can be staggering. We're talking terabytes daily in large systems.
Wow.
And that volume directly translates to cost, ingestion costs, storage costs. It adds up fast.
And the noise factor.
Yeah, if you just log everything without thinking, without structure, you can easily create a data swamp. It's just too much noise, makes it impossible to find the actual signal, the important information. And that leads to alert fatigue, where people just start ignoring alerts because there are too many false positives. And managing the pipeline itself.
That's another thing. Deploying agents, scaling the processing layer, managing the storage backend, it's a significant operational burden, especially if you're self-hosting.
So how do people typically set this up? There are cloud options and open source, right?
Exactly. The major cloud providers, AWS, Azure, GCP, all offer managed logging services. You've got AWS CloudWatch logs, Azure Monitor logs, and Google Cloud Logging. They handle a lot of the scaling and management for you.
How do they work generally?
They usually provide agents you install on your VMs or run as sidecars in containers. They collect logs, send them to the central service. Then you get powerful query languages like CloudWatch Logs Insights, Azure's KQL, or querying GCP logs in BigQuery, plus dashboards and alerting integrations.
Makes sense. And the classic open source route.
That's traditionally been the ELK stack. Elasticsearch for storing and indexing, Logstash for processing and enrichment, and Kibana for visualization and dashboards. You typically use agents like FileBeat to ship the logs from your sources to Logstash or directly to Elasticsearch.
Still popular.
Very. But it comes with that operational overhead. You have to manage the scaling, upgrades, and maintenance of all those components yourself. It's powerful, flexible, but requires engineering effort. Also, OpenTelemetry is increasingly playing a role here too, offering vendor-neutral ways to collect and export logs.
Architecturally, what does a typical logging pipeline look like? The stages involved.
Sure. Generally, you have four main stages. First, collection, getting the logs off the source systems using agents or SDKs. Second, processing enrichment. This is where you parse the logs, maybe from plain text into structured JSON, add context like Kubernetes metadata, or crucially trace IDs, and maybe filter out noise. Logstash is often used here. Third, storage indexing. Storing the process logs in a system built for searching time series data like Elasticsearch or OpenSearch. And fourth, analysis visualization, using tools like Kibana, Grafana, or the cloud provider dashboards to query, explore, and visualize the log data.
Okay, collection, processing, storage, analysis, got it. And operationally, you mentioned cost. Retention must be a big factor there too. How long do you keep this stuff?
It's a huge balancing act. You've got compliance requirements, regulations like IPA or SOX might mandate keeping logs for 6 or 7 years.
8 years.
Yeah. But operationally, for active troubleshooting, you might only need, say, 30, 60, maybe 90 days of logs readily searchable. Keeping terabytes searchable for years gets incredibly expensive.
So what's the solution?
Tiered storage. You keep recent logs in hot storage, fast, searchable, but more expensive. Then you automatically move older logs to warm storage, less performant, and eventually to cold or archival storage like AWS S3 Glacier, Azure Blob Archive, or GCP Coldline. It's super cheap for long-term retention, but slow to retrieve if you ever need it for an audit. Automation, using things like Elasticsearch's ILM policies or cloud provider lifecycle rules, is absolutely key here.
Makes sense. And alerting on logs, you mentioned alert fatigue. How do we avoid just drowning in notifications?
The key is to alert on actionable signals. Don't just fire an alert every time you see an error log message. That's useless.
So what do you alert on?
You look for patterns, rates, thresholds that indicate a real problem. Maybe a sudden spike in 5xx server error logs for a specific service, or a certain security-related log pattern appearing multiple times quickly. Use aggregation, alert if the rate of errors exceeds a threshold over a time window, and correlate alerts using trace IDs where possible group-related errors together instead of firing dozens of separate alerts for one bad request.
The goal is, if an alert fires, someone actually needs to look at it.
Exactly. It'd have to mean something important is likely happening.
Okay, so best practices for centralized logging, the absolute must-dos.
Number 1, use structured logging. JSON is the standard. It makes automated parsing reliable. Don't just log strings of text. Be consistent with your schema across services. Use standard field names for things like timestamp, service name, severity. Include rich context, host name, region, user ID, if appropriate and safe, and critically, the trace ID. That trace ID links logs to traces. Manage your log levels effectively. Log verbosely in dev, less in prod, but have the ability to dynamically change levels for specific services if you need to debug something in production without redeploying. And always, always centralize. Detach logs from the compute instances.
Right, and the big mistakes, the anti-patterns to avoid.
Logging sensitive data is the cardinal sin. PII, passwords, API keys, never log that stuff plain text. It's a massive security risk and compliance failure. Excessive verbosity in production logging, debug, or trace messages all the time just creates noise and cost. Inconsistent or unstructured formats make analysis impossible at scale. Over-alerting, as we discussed, leads to fatigue. People will start ignoring pages if they cry wolf too often. And finally, treating logging as an afterthought. If you don't design logging in, you won't have the information you need when things inevitably break.
Any quick examples of companies getting real value from this?
Sure. There are case studies like Hapag-Lloyd, the shipping giant. They used AWS OpenSearch to centralize logs, which dramatically cut down their troubleshooting time and even gave them new business insights from analyzing operational data. Or Infor, a business software company, managing huge volumes like 12 terabytes a day using Sumo logic. They implemented smart tiering and analysis, saving them reportedly over $1 million a year and thousands of developer hours just by reducing MTTR.
Shows it's more than just finding errors.
Definitely. It's about operational intelligence.
Okay, let's shift gears. From operational logs to something more specific, audit logging.
Right. This is less about general debugging and more about security, compliance, and accountability.
This is the who did what when record, right? The immutable one.
Ideally, yes. An audit log, or audit trail, is a security-relevant chronological record of events and changes within a system. Think user logins, password changes, permission updates, admin actions, critical data access or modification. The problem it solves is that regular operational logs often lack the specific details, the security context, or the guaranteed retention and integrity needed for compliance audits or forensic investigations.
So this is really driven by regulations and security needs.
Primarily, yes. Things like GDPR, HIPAA, SOX, PCI DSS often explicitly require audit trails for certain actions. They're also crucial for post-incident forensics, reconstructing the timeline of a security breach, and for detecting potential insider threats or simply ensuring accountability for administrative actions.
What are the challenges here, similar to general logging?
Some similarities, but also distinct challenges. Data volume can again be very high, especially if you need to log every time sensitive data is accessed, like patient records. And retention requirements are often much longer, years, not months. That means significant long-term storage cost. Performance overhead can be a concern if audit logging happens synchronously within critical paths, but the biggest challenge is ensuring the integrity and security of the audit logs themselves. They need to be tamper-evident or tamper-proof, and access needs to be strictly controlled. Building that secure pipeline is complex.
How do the cloud platforms handle this? Do they have dedicated services?
They do. They typically provide services that automatically capture platform-level API activity. AWS has CloudTrail, which logs almost all AWS API calls. Azure has Azure Activity Log for subscription-level events and resource-specific auditing. GCP has Cloud Audit Logs integrated across the platform.
What kind of events do they capture by default?
Usually management events, things like creating a VM, changing a firewall rule, modifying IAM permissions, these are typically enabled by default. Capturing data access events like reading an object from a bucket or querying a database is often optional because it generates much higher volume, but it's critical for many compliance scenarios.
And where do these logs go?
You configure them to be sent to secure, long-term storage, often dedicated storage buckets like S3 or GCS, in a separate lockdown security or log archive account. From there, you might stream them to a SIM system, security information, and event management for real-time analysis and alerting on suspicious activity.
Architecturally, what's key for audit logs? Security, security, security.
Absolutely. The pipeline needs to be secure end-to-end. Secure transport using TLS, storage that's tamper-evident, maybe using write once, read many warm features like S3 Object Lock or CloudTrail's log file integrity validation, and critically, access control. Only a very small authorized group should ever be able to access or manage the raw audit logs. Use least privilege, require multi-factor authentication, MFA, and you should even audit who accesses the audit logs.
They're net auditing.
Kind of, yeah. You need to ensure the audit trail itself is trustworthy. And try to make it difficult or impossible for someone, even an admin, to disable audit logging without leaving a trace. Cloud platforms often have mechanisms like AWS Organization's SCPs to help enforce this.
Operationally, retention and tamper resistance seem paramount.
They are. Retention is usually dictated by the longest relevant compliance requirement, often 6 or 7 years. Tiered storage is essential for managing cost over that duration. Tamper resistance techniques like the cloud provider features or cryptographic hashing for custom logs must be implemented. And real-time alerting on critical audit events is vital. Don't just log and forget. Stream logs to a SIEM and set up high-priority alerts for things like someone disabling CloudTrail, major IAM policy changes, multiple failed login attempts, access to highly sensitive data, creation of new admin users. These should trigger an immediate incident response.
Okay, best practices for audit logging.
Define a clear, explicit audit policy based on your risk assessment and compliance needs what must be logged. Centralize your audit logs, ideally in a dedicated, highly secured account separate from your main operational accounts. Use structured formats like JSON for easier automated analysis by SIEM tools. Implement fail-safe mechanisms where possible. If audit logging fails, should access be denied. That's a tough trade-off, but important for critical systems. And as mentioned, audit the auditors. Monitor access to the audit logs themselves.
And the anti-patterns. Things to definitely avoid.
Having incomplete logs missing critical events like failed logins or, very commonly, not enabling data access logging when needed for compliance. Storing audit logs locally on the systems generating them, where they can be easily altered or deleted by an attacker who gains access. Dispersion is bad here. The log and forget mentality, collecting logs purely for compliance checkbox purposes without any real-time monitoring, alerting, or investigation based on them. They become useless shelfware.
Got it. Okay, let's move on. We've covered what happened with logs, who did it with audit. Now let's tackle performance and the why with distributed tracing.
Exactly. This pattern is absolutely essential for understanding behavior in complex distributed systems, especially microservices.
It helps navigate that maze you mentioned earlier.
It really does. So, a distributed trace essentially follows the journey of a single request. Maybe a user clicking a button on a website as it travels through all the different services involved in fulfilling that request. Each piece of work done by a service in the context of that request is recorded as a span. A span has a start time, a duration, metadata, and links to its parent span.
And the problem this solves is figuring out why something was slow or failed.
Precisely. Imagine a checkout process that calls 5 different microservices. If it's slow, which one is the culprit? Is it service A or maybe service C calling service D? Without tracing, it's incredibly difficult, often just guesswork. Tracing reconstructs that entire call chain visually. You often see it as a timeline or a flame graph. It immediately highlights where the time was spent or where an error occurred. It directly answers why was this specific request slow or why did it fail.
So it must dramatically speed up root cause analysis, right?
Hugely. It slashes mean time to repair, MTTR. It's also fantastic for performance optimization. You can easily spot unexpected bottlenecks or services introducing high latency. It can even help you automatically generate a map of your service dependencies just by observing the trace data.
Okay, sounds amazing. What are the trade-offs? It sounds data intensive.
That's the main one, massive data volume. If you tried to trace every single request in a high-traffic system, you'd generate an enormous amount of trace data, far more than logs, often.
So cost becomes an issue again.
A big issue. Both storage cost and processing cost for the backend. This makes sampling almost unavoidable in most systems.
Sampling. Deciding which requests to trace.
Exactly. But sampling is tricky. If you just sample randomly, say 1% of requests, you might miss the rare but critical errors or slow requests you actually care about. So sampling strategies get sophisticated. Other trade-offs include instrumentation overhead. You need to add tracing libraries, SDKs to your application code. Auto-instrumentation helps, but isn't always perfect, and propagating the trace context, that trace ID and parent span ID across different network protocols, asynchronous boundaries like message queues, and potentially across code written in different languages, that can be complex to get right.
What are the main tools people use for tracing?
The big movement now is around OpenTelemetry, often abbreviated OTel. It's a CNCF project providing standardized, vendor-neutral APIs, SDKs, and protocols for generating and collecting telemetry, data traces, metrics, and logs.
So instrument once, send anywhere.
That's the goal. You instrument your applications using OpenTelemetry libraries, and then you can configure an OTel collector to receive that data using the OTLP protocol and export it to various backends. A very popular open source backend for traces is Jaeger, another CNCF project. It stores trace data, often in Elasticsearch or Cassandra, and provides a web UI for visualizing the traces.
And the cloud providers.
They all have managed tracing services too. AWS X-Ray is tightly integrated with AWS services. Azure Application Insights includes tracing capabilities and is increasingly embracing OpenTelemetry as the standard way to get data in. GCP Cloud Trace is Google's managed service, also recommending OpenTelemetry for instrumentation.
You mentioned the life cycle of a trace involving context propagation. Can you walk through that flow?
Sure. It typically starts when a request first enters your system, maybe at an API gateway or front-end service. That service generates a unique trace ID for the entire request and creates the first root span. Then, whenever that service makes a call to another downstream service, for example, via HTTP or gRPC, it injects the trace ID and its own span ID into the request headers. Standards like the W3C trace context define how these headers should look.
So the context travels with the request.
Exactly. The downstream service extracts these IDs from the headers. It knows it's part of an existing trace, identified by the trace ID, and knows which span was its parent, using the incoming span ID. It then creates its own child span, recording its work. This continues through the entire call chain. Each service creates spans and propagates the context.
And where do the spans go?
Usually, spans are sent asynchronously out of band from the application or a local agent to a central collector, like the OTel collector. This collector might batch them, add more metadata, and then forward them to the tracing backend, like Jaeger or X-Ray. The backend then receives all these individual spans from potentially many different services and reassembles them using the trace ID and parent-child relationships into the complete trace for visualization.
That propagation sounds like a place things could easily break.
It is, especially across message queues or other async boundaries, or between services using different instrumentation libraries. Getting context propagation working reliably everywhere is often the hardest part of implementing tracing.
Let's talk about sampling again. You said random isn't always great. What are the main strategies?
Broadly, there are two main types: head-based and tail-based. Head-based sampling makes the decision whether to trace a request right at the beginning when it first enters the system. It's simple, low overhead because you only collect spans for the requests you decide to sample.
For the downside.
It's dumb. It doesn't know if the request will eventually fail or be slow downstream, so you might decide not to sample a request that later turns out to be really interesting because it erred out 5 services deep.
Okay, so tail-based.
Tail-based sampling collects spans for all requests temporarily. The sampling decision is made after the entire trace has completed and all its spans have been gathered, usually at the collector level. This allows for much smarter decisions. You can implement policies like always sample traces that contain an error, or sample all traces longer than 1 second, or sample 10% of successful traces, but 100% of errors.
That sounds much better for catching problems.
It is, but the trade-off is complexity and resource usage. You need infrastructure capable of buffering and processing spans for 100% of your traffic, even if you ultimately only store a fraction of it. It's much more expensive and harder to operate.
So maybe a hybrid approach.
Often, yes. Maybe some basic head sampling at the edge to shed load, combined with more intelligent tail sampling centrally.
Best practices for making tracing effective.
Standardize on open telemetry if you can. It gives you vendor neutrality and a huge ecosystem. Start by instrumenting your most critical user journeys or business transactions first. Don't try to boil the ocean immediately. Enrich your spans with useful, low cardinality attributes, things like service version, API endpoint, customer tier maybe. Avoid putting high cardinality data like user IDs or request IDs directly into indexed span attributes, as it can overload the backend. Use clear, consistent names for your spans. And critically, integrate the 3 pillars. Make sure your trace ID appears in your logs for easy correlation. Use metric exemplars linking a specific metric data point, like a latency spike, back to example traces that contributed to it. That trace ID is the glue.
A Rosetta Stone, almost?
Exactly. And the anti-patterns for tracing. The biggest killer is incomplete or broken traces where context propagation fails somewhere. If you can't see the whole journey, tracing loses most of its value. Over-instrumentation and creating too many spans, maybe for tiny internal functions, can add overhead and noise. Naive sampling strategies that consistently miss important error traces. You must find ways to preferentially sample or keep traces associated with errors or high latency. And again, like logs, avoid logging sensitive data within your span attributes.
Any famous examples of tracing being crucial?
Well, Uber basically invented Jaeger because they needed it so badly to manage their thousands of microservices. They built tracing into their core RPC framework, making it almost automatic for developers, which was key for adoption. Their experience shows that at massive scale, tracing isn't just helpful, it's a fundamental requirement for operating the system. They've also done a lot of work on adaptive sampling to handle traffic seasonality and optimize costs.
Fascinating. Okay, next pattern, metrics aggregation.
Right. Moving from individual request journeys back to the big picture, the numbers.
This is where we get the graphs on dashboards, the alerts for high CPU, error rates, that kind of thing.
Precisely. Metrics are numerical measurements collected over time. Think request counts, latencies, error rates, queue depths, CPU utilization, memory usage. They're typically aggregated, summed, averaged, calculated as percentiles, and stored as time series data. A time series is identified by a metric name, HTT prequest total, and a set of key value pairs called dimensions or labels. Example, service auth method post status code 500.
And a problem they solve is efficiency.
Largely, yes. Trying to analyze raw event logs or traces to understand overall system health, like what's the average site latency right now, is incredibly inefficient or even impossible at scale. Metrics provide a compact, pre-aggregated numerical summary.
So you can quickly see trends in overall status.
Exactly. Metrics are incredibly efficient for storage and querying. Time series databases, TSDBs, are specifically optimized for this. They're powerful for dashboards, identifying trends, establishing performance baselines, and driving alerting based on numerical thresholds. And crucially, metrics are the foundation for defining and monitoring service-level objectives, or SLOs.
We'll come back to SLOs. What are the trade-offs with metrics compared to, say, logs or traces?
The main one is loss of granularity. A metric tells you the average latency was 500 meters or the error rate was 2%. It doesn't tell you which specific requests were slow or failed. You lose the individual event details. For that, you need to pivot back to traces or logs, hopefully using that trace ID correlation.
You have to decide what to measure beforehand.
Generally, yes. Metrics are predefined. You need to instrument your code or configure your systems to emit the specific numbers you care about. It's less exploratory than searching through logs where you might discover unexpected patterns. And the other big challenge with metrics is,
Let me guess, high cardinality.
you got it, the cardinality explosion. If you use labels with too many unique values, think userid, requested, containerid, the number of unique time series combinations can explode exponentially. If a metric has 5 labels and each label have 100 possible values, that's 1,005, or 10 billion potential time series for just that one metric. This can overwhelm even robust TSDBs, causing high memory usage, slow queries, and massive costs. Managing cardinality is critical.
What are the common tools people use for metrics?
In the open source world, Prometheus is the de facto standard. It works on a pull model. It scrapes HTTP endpoints exposed by your services that list metrics in a specific format. Prometheus has its own TSDB, a powerful query language called PromQL, and integrates with Alert Manager for handling alerts. Grafana is almost always used alongside Prometheus for building dashboards.
And the cloud providers.
They all have their own integrated metrics services: AWS CloudWatch metrics, Azure Monitor metrics, and GCP Cloud Monitoring. These automatically collect a wide range of metrics from their respective cloud resources, VMs, databases, load balancers, etc. They also let you ingest custom metrics from your applications, often via agents or SDKs, sometimes using push-based APIs. They provide their own query tools, dashboarding, and alerting capabilities.
Managed Prometheus is also a thing now in the cloud, right?
Yes, exactly. Services like AWS Managed Service for Prometheus, Azure Monitor Managed Service for Prometheus, and GCP Managed Service for Prometheus offer a managed Prometheus experience, handling the scaling and operational burden while letting you use standard PromQL and Grafana.
You mentioned Prometheus uses a pull model, while cloud services often use push. Can you elaborate?
Sure. Pull model, Prometheus. The central Prometheus server periodically sends requests to configured targets, your services, asking for their current metrics. Pros: simpler client-side config, central control over scraping, easy to detect if a target is down, scrape fails. Cons: can be tricky with firewalls, service discovery is needed, not great for very short-lived jobs. Push model, CloudWatch agent, stats D. The client, your application or an agent, actively sends metrics to a central endpoint. Pose: works well for ephemeral job serverless functions, simpler and complex network topologies. Cons: can potentially overwhelm the ingestion endpoint, client needs endpoint config, harder to detect if a client silently stops sending metrics.
So different trade-offs, and you mentioned Prometheus itself isn't always enough for high availability or long-term storage.
Right. A single Prometheus server stores data locally and isn't inherently HA. For serious production use, especially long-term storage and global query views, people often use systems on top of Prometheus, like Thanos or Cortex, or its successor, Mimir. Thanos uses a sidecar model where each Prometheus uploads its data blocks to object storage, like S3. A global querier component can then query data across multiple Prometheus instances and the object store for long-term data. Cortex Mimir used Prometheus's remote write feature to push data to a central, scalable multi-tenant cluster that handles ingestion, storage, and querying. They offer different architectural approaches to achieve scalability, HA, and long-term retention for Prometheus metrics.
Okay, back to operations. Managing high cardinality labels, how do you actually do that?
It's tough. First, you need to be aware of the cardinality of your labels. Calculate it. Multiply the number of unique values for each label attached to a metric. Then, actively manage it. Strategies include aggregation instead of userid, maybe use user tier, free paid enterprise. Normalization for things like HTTP paths, use templates, users userid, instead of the raw path, users 1, 2, 3, 4, 5, as a label value. Use histograms or summaries for things like latency, these capture distributions, without needing a unique time series per request duration. Drop unnecessary high cardinality labels entirely, and establish cardinality budgets or limits for teams or services to prevent accidental explosions.
You also mentioned SLOs, service level objectives. How do metrics feed into those?
Metrics are the raw ingredients for SLOs. You first define a service level indicator, SLI. This is typically a metric or a ratio of metrics, representing a key aspect of service health. For example, an SLI could be the proportion of successful HTTP requests, calculated as good requests, total requests, or the percentage of requests served faster than 300 meters, often derived from a histogram metric.
So the SLI is the measurement.
Right. Then the service level objective, SLO, is the target value for that SLI over a specific time window. For example, 99.9% of HTTP requests will be successful over a rolling 30-day period, or 95% of homepage requests will complete in under 500 meters over a rolling 7-day period.
Yeah.
You track your SLI metric against the SLO target. This gives you a clear, objective measure of reliability from the user's perspective. The difference between 100% and your SLO target gives you your error budget, how much unreliability is acceptable within that window.
And that error budget can drive alerting.
Exactly. That's a much more effective way to alert than just setting static thresholds on raw resource metrics. Alert when your service is burning through its error budget too quickly. This directly ties alerts back to user-impacting reliability targets.
So for alerting best practices, alert on symptoms, use error budgets, anything else?
Alert on symptoms affecting users, like the site being slow or returning errors, not necessarily on the underlying causes, like high CPU, unless they are predictive of symptoms. An alert should be actionable. If you get paged, you should know what's likely impacted and have a general idea of how to respond. Avoid noisy alerts, tune thresholds, and time windows carefully.
Makes sense. Best practices overall for metrics.
Use standard naming conventions makes metrics easier to find and understand. Instrument your code properly using client libraries. Use labels effectively for dimensions, group-related things. Allow slicing and dicing, but be mindful of cardinality. Prefer histograms over summaries for things like request latency if you need to aggregate them across instances. Use Prometheus recording rules to pre-compute complex or expensive queries.
And the metrics anti-patterns.
Collecting vanity metrics, things that look good on a dashboard but don't actually reflect user experience or business outcomes. Using metrics for individual performance tracking or micromanagement, terrible for team morale and often misleading. Ignoring qualitative feedback metrics don't tell the whole story. Talk to users, look at support tickets, and the big one we keep hitting, using high cardinality labels without understanding the impact. Don't use unbounded values like unique IDs as label values.
Got it. Okay, final pattern. Health checks and endpoint monitoring.
Right. This one feels simpler maybe, but it's absolutely fundamental for automated systems, especially load balancing and orchestration.
This is the health endpoint we often see.
Exactly. A health check endpoint is typically a dedicated HTTP endpoint, like health status ready that a service exposes. External systems like load balancers, Kubernetes, service discovery tools query this endpoint periodically to determine if an instance of the service is not just running, but actually healthy and capable of serving traffic correctly.
Why isn't just checking if the process is running or the port is open enough?
Because a service can be running, accepting TCP connections, but still be unable to function properly. Maybe its connection pool to the database is exhausted. Maybe a critical downstream dependency is unavailable. Maybe it's stuck in a deadlock or has run out of memory internally. If a load balancer just does a simple TCP check, it might keep sending traffic to this zombie instance, causing errors for users. The health check endpoint allows the application itself to report its true internal state and ability to serve requests.
Okay. And you mentioned different kinds of checks, particularly in Kubernetes.
Yes, Kubernetes formalizes this with different probe types. Liveness probes ask, is this container fundamentally okay? Should it be restarted if it fails this check? A failure here tells Kubernetes the container is deadlocked or unrecoverable and needs to be killed and replaced. Readiness probes ask, is this container ready to accept new traffic right now? A failure here tells Kubernetes to stop sending traffic to this pod by removing it from the service endpoint, but doesn't necessarily mean the container needs restarting. It might just be temporarily busy, waiting for a dependency, or still initializing. Startup probes, newer, are used for applications that take a long time to start, disabling the other probes until the app signals it's fully up.
What are the main benefits and maybe trade-offs here?
The benefits are huge for reliability and availability. Health checks allow automated systems to detect unhealthy instances quickly and remove them from rotation, preventing user impact. They enable automated self-healing Kubernetes, restarting failed containers based on liveness probes. They're essential for graceful deployments, like rolling updates or blue-green, and scaling, ensuring new instances are fully ready and healthy before receiving production traffic, allowing for zero downtime changes.
Any trade-offs?
Maybe the distinction between active versus passive checks. Active checks, like kubelet probes or load balancer checks, periodically query the endpoint. Pros: can detect when a service recovers. Cons: add some load. Detection has some delay based on the interval. Passive checks, like circuit breakers analyzing real traffic, might detect failures faster with no extra load, but can't easily detect recovery without some active probing component. Combining them is often best.
How are these implemented in practice, say in K8s or the cloud?
In Kubernetes, you define liveness, readiness, and startup probes right in your COD or deployment manifest, YAML. You specify the check type, HTTP GT, TSP socket, command execution, even gRPC, the path port command, and parameters like initial delay seconds, period seconds, timeout seconds, failure threshold. Kubelet on the node runs these probes. Cloud load balancers, AWS Elebol, BNLB, Azure Load Balancer, GCP Cloud Load Balancing, have similar health check mechanisms. You configure them at the target group or backend service level, specifying protocol, port, path, intervals, timeouts, and healthy-unhealthy thresholds. The load balancer only routes traffic to targets that pass these checks.
What are the important knobs to tune when configuring these operationally?
Getting the timing right is crucial. The interval, how often to check, needs to balance timely detection with overhead. The timeout, how long to wait for a response, must be less than the interval and accommodate normal fluctuations. The failure threshold, how many consecutive failures mark an instance unhealthy, should almost always be greater than 1, maybe 2 or 3, to avoid triggering on transient network blips or brief slowdowns. Setting it to 1 can lead to unnecessary restarts or traffic shifts. You might also need to differentiate the severity of dependency checks. Does failure to reach a non-critical caching service mean the whole instance is unhealthy? Maybe not. Your readiness check logic might need to reflect degraded states.
Okay, best practices for health checks.
Keep them lightweight and fast. A health check shouldn't consume significant resources or perform complex operations itself. Check critical dependencies, but do it carefully. Verify the database connection pool is healthy, perhaps, but use short timeouts. Typically, dependency checks belong in readiness probes, not liveness probes. Implement separate liveness and readiness probes with different logic. Liveness should check for truly unrecoverable states requiring a restart. Readiness checks if the instance can serve traffic now, considering dependencies and initialization. Use a dedicated standardized endpoint like health or ready. Secure your health check endpoints if they expose any sensitive info or if they're reachable externally. Usually they should only be accessible from the orchestrator or load balancer IPs.
And the health check anti-patterns, what not to do.
The classic bad one, the database ping liveness probe. Putting a check to the database in your liveness probe means if the database has a temporary issue, Kubernetes might restart all your application instances, causing a cascading failure or thundering herd problem when they all try to reconnect. Use readiness for this. Health checks with heavy logic that are slow, prone to timeouts, or can fail themselves, leading to false negatives. Ignoring application startup time. If your liveness probe starts checking before the app is fully initialized, it might kill the container prematurely. Use startup probes or appropriate initial delays. Using the wrong type of check, like a simple TCP check when you really need an HTTP check to verify the application logic, is working.
Any real-world examples where health checks were critical during incidents?
Absolutely. If you read outage postmortems from major companies, like Slack has published in the past, load balancer health check failures are often a key indicator or symptom when widespread network or service degradation occurs. They're often the first signal automated systems see that something is fundamentally wrong across a fleet. Sometimes load balancers even have panic mode failsafes. If too many instances fail health checks simultaneously, they might start routing traffic even to unhealthy ones to avoid total system collapse. It shows how critical that health signal is.
Wow. Okay, so that's the 5 patterns. Centralized logging, audit logging, distributed tracing, metrics aggregation, and health checks.
Yep, we covered a lot of ground.
It's a lot to take in. And you've emphasized that the real power comes when you use them together, right?
Absolutely. They aren't isolated tools, they're complementary parts of a larger observability strategy. True observability comes from weaving them together. Think about a typical incident workflow. A health check fails, taking an instance out of rotation. Metrics dashboards show the impact, maybe error rates spike, latency increases. Distributed tracing helps you pinpoint the specific faulty downstream service or slow database query causing the problem for affected requests. Logs, correlated using the trace ID you found in the trace, give you the detailed error messages and context around what went wrong inside that specific service instance. And audit logs might show if a recent deployment or configuration change coincided with the start of the issue.
And the trace ID is the key linking them.
It's often the crucial piece of glue connecting the data across logs, traces, and even sometimes metrics via exemplars.
It really is like having different lenses, different levels of zoom to understand the same complex system. We also touched quite a bit on the choice between using managed cloud services versus rolling your own with open source tools.
Right. It's a constant trade-off. Managed services generally offer lower operational overhead, tighter integration with the cloud platform, and often a faster time to value. You offload the scaling and maintenance burden. Open source gives you more flexibility, control, avoids vendor lock-in, and can be more cost-effective at very large scale, but it requires significant engineering investment to build, operate, and maintain reliably.
But it feels like things are converging somewhat, especially with open telemetry.
Definitely. Open telemetry is a game changer here. By standardizing the instrumentation, how you get data out of your applications, it makes it easier to switch backends or use a mix of tools without rewriting all your application code. It promotes that vendor neutrality.
Looking forward, what's the next big thing in this observability space? Where is it heading?
I think it's clearly heading towards leveraging AI and machine learning much more heavily. AI ops, AI for IT operations. The sheer volume and complexity of observability data generated by modern systems is becoming overwhelming for humans to analyze manually. AML is needed to automate the correlation across signals, detect anomalies, predict potential issues before they impact users, and even assist in or automate root cause analysis and remediation.
So the job shifts, maybe less time spent manually digging through dashboards and logs during an incident.
And more time spent building, training, and refining the intelligent systems that can do that analysis faster and potentially more accurately. That seems to be the direction. The focus shifts up the stack from collecting data to deriving automated insights and actions from it.
That was a really fantastic, comprehensive deep dive into these critical patterns. Thank you so much for walking us through all of that.
My pleasure. It's complex stuff, but getting a handle on these patterns is just essential if you want to build and run reliable software today.
And to you, our listener, if you found this deep dive valuable, and I certainly did, make sure you subscribe to Joy of Architecture so you don't miss our future explorations into what makes modern systems tick and sometimes what makes them break.
And as you think about implementing these patterns in your own systems, maybe consider this. The increasing complexity of distributed systems is really forcing a fundamental shift. We're moving away from just monitoring for known failure modes and reacting to them. We're moving towards true observability, the ability to proactively understand unknown states, ask arbitrary questions, and even predict emergent issues. Especially as AI starts handling more of the routine analysis, what does this shift really mean for how we need to design, build, and operate software in the future?
A fascinating question to ponder. Thanks again, and join us next time for another deep dive.